For over 50 years, the silent, invisible backbone of America's land-based nuclear deterrent has rested on a fleet of aging giants, the Minuteman III Intercontinental Ballistic Missiles, ICBMs. Hidden in reinforced concrete silos beneath the rolling wheat fields and snowy plains of the American Midwest, these missiles have stood watch since the height of the Cold War. Launched in the 1970s and originally designed for a modest 10-year operational lifespan, these missiles are now nearly half a century old, well past their intended expiration date. As of early 2026, the Pentagon has officially moved beyond the era of patchwork maintenance and into a high-stakes make-or-break transformation known as the LGM-35 Sentinel program. This is not merely an upgrade, it is a ground-up reinvention of the most destructive leg of the U.S., a nuclear triad. However, the path to modernization is paved with unprecedented financial and logistical hurdles. The Sentinel program is currently caught in a massive fiscal storm that has rocked Washington. Originally estimated at a staggering $78 billion, the projected life cycle cost has recently ballooned to $141 billion, an 81% increase that triggered a critical breach of the Nunn-McCurdy Act, a federal law designed to flag programs that have spiraled out of control. Despite the intense sticker shock, the U.S. government has made a definitive choice. The program is too vital to fail. In the fiscal year 2026 budget, funding for the Sentinel alone has surged to $5.3 billion. This includes $4.1 billion dedicated strictly to research and development, R&D, and supplementary reconciliation funds to keep the golden age of nuclear modernization from collapsing under its own weight. So, how do you replace an entire nuclear fleet while it remains on 24/7 high alert? To understand the answer, we have to look inside the high-tech factories of Utah and the crumbling underground silos of Montana, where the next 50 years of global deterrence are being built. The anatomy of a modern ICBM, digital birth. The Sentinel is not just a Minuteman IV, it is a fundamental departure from the analog era. While the Minuteman III relies on 1960s-era vacuum tubes, magnetic tape, and hardwired circuits, the Sentinel is the first major nuclear weapon built on a digital twin architecture. This means that before a single piece of carbon fiber was spun or a single bolt was turned, a perfect virtual replica of the missile existed in a supercomputer. Engineers can simulate every flight condition, from the vibration of launch to the extreme heat of atmospheric re-entry, identifying flaws before they ever reach the factory floor. The physical missile is a three-stage, solid-fuel behemoth designed for modularity. The warhead. The Sentinel will carry the newly developed W-87-1 thermonuclear warhead. This is housed inside a Lockheed Martin-built Mk-21A re-entry vehicle. Unlike older designs, this re-entry vehicle is built with modern materials that can withstand more erratic flight paths, making it harder for modern missile defenses to intercept. The brain. The missile features a plug-and-play guidance system. In the past, updating a missile's flight software required physical hardware changes. The Sentinel's modular brain is designed to be updated via secure software uploads, ensuring the missile can overcome future adversarial defenses without needing a complete physical rebuild every decade. The muscle. The Sentinel relies on massive solid rocket motors, SRMs. Because the missile must sit in a silo for decades and then ignite perfectly in seconds, solid fuel is the only option. However, the consistency of this fuel must be absolute. Any tiny air bubble or crack in the fuel grain could cause the missile to explode on the launch pad. The carbon fiber winding process, spinning a superweapon. The heart of the Sentinel's production lies in Promontory, Utah, at Northrop Grumman's Strategic Missile Test and Production Complex. On this facility is a cathedral of modern aerospace engineering. Here, the manufacturing of rocket motor casings has transitioned from the heavy welded steel of the 1970s to high-strength, lightweight carbon fiber composites. The mandrel. A massive rotating mold called a mandrel, perfectly shaped like a rocket stage, is placed on a specialized winding machine. This mandrel acts as the skeleton for the carbon fiber. The precision spin. Thousands of individual strands of carbon fiber, each thinner than a human hair but stronger than steel, are pulled through a chemical bath of high-performance epoxy resin. And these resin-soaked fibers are then pulled through a guide and wound onto the rotating mandrel. Cross-angle strength. This is the critical engineering step. To ensure the casing can survive the intense internal pressures of solid fuel combustion, which reaches thousands of pounds per square inch, the fibers are wound at precise, alternating angles, often plus or minus 55 degrees and plus or minus 20 degrees. This creates a diamond weave, or geodesic pattern. This structure is significantly lighter than steel, which allows the Sentinel to carry a heavier payload or reach a longer range with the same amount of fuel. Curing the shell. Once the winding is complete, the entire stage, which can be over 30 feet long, is placed into a massive industrial oven called an autoclave. Under intense heat and pressure, the resin hardens, turning the flexible fibers into a rigid, flight-ready shell. The $141 billion silo crisis, beyond the missile. Perhaps the most shocking revelation of the Sentinel program is that the biggest driver of the cost surge isn't the missile itself, it's the dirt and concrete infrastructure. The U.S. maintains 450 active silos, spread across North Dakota, Montana, Wyoming, Colorado, and Nebraska. These silos are connected to 45 launch control centers via a web of underground cables. Initially, the Air Force hoped to simply refresh the old Minuteman III silos, a coat of paint and some new electronics. However, as inspections began in 2024 and 2025, the grim reality set in. The 55-year-old concrete is cracking, the steel is corroding, and the water tables have shifted. The utility corridors. To connect the new Sentinel missiles to their command centers, the Air Force must bury thousands of miles of new fiber optic cables. This requires negotiating with thousands of private landowners across 5 states and digging through some of the most remote terrain in the country, all while maintaining nuclear-grade security protocols. The back-to-the-studs rebuild. As of 2026, the plan has shifted from a refresh to a total reconstruction. Each silo must be excavated, the old electronics stripped out, and new environmental control systems installed to keep the Sentinel's digital brains from overheating. The SADAF milestone. In late 2025, the Air Force reached a historic milestone by taking its first Minuteman III silo completely offline to begin the transition. And this Site Activation Task Force move is a visible sign that the concrete and steel phase of the program is finally here, turning the American Midwest into the largest construction site on Earth. The silicon logic of strategic deterrence. Just as the Sentinel relies on the W-87-1 Warhead and Mk-21A re-entry vehicle to align with microscopic precision, the global high-end semiconductor industry relies on a hyper-controlled supply chain to ensure every microchip is identical across millions of units. The tolerance standard. In a semiconductor fabrication plant, high-tech sensors measure the purity of silicon wafers to within a single atom. This is the same level of mass calibration precision used by Northrop Grumman to measure the solid propellant pour in a Sentinel rocket stage. In both cases, a 1% deviation leads to a systemic failure, either a ruined batch of processors or a catastrophic launch failure. On thermal integrity, semiconductor manufacturing uses precise thermal cycles to etch circuits into silicon without damaging the material. Similarly, the curing chambers for the Sentinel's carbon fiber skin use an autoclave to ensure the chemical bonds of the resin reach maximum strength. This temperature-controlled environment ensures the structural integrity of the missile doesn't degrade, even after decades of sitting in a silo. The zero-defect assembly. In modern aviation, engines are assembled using agile manufacturing, where every bolt is torqued by a robotic arm and logged into a digital database. In 2026, the Air Force is adopting this digital thread model. By using modular components that snap together with computer-verified accuracy, they can assemble and deploy missiles with unprecedented speed, ensuring the replacement of the Minuteman fleet stays on a relentless, error-free timeline. The Sentinel program relies on precision-calibrated manufacturing systems similar to advanced rocket and aerospace engineering. The Sentinel's watch. The $141 billion Sentinel gamble is a bet on the long term. It is a statement to the world that the American land-based deterrent will remain a factor until the end of the 21st century. With the first test flight now scheduled for March 2028 and initial operational capability targeted for the early 2030s, The US is in a desperate race to ensure its nuclear shield doesn't rust away before its replacement is ready. The budget of $5.3 billion for 2026 is just the down payment on a future where the Sentinel stands guard until the year 2075. And it is a monumental task that combines the heavy-duty craftsmanship of 19th century construction with the digital carbon fiber precision of the 21st century. What do you think? Is this nuclear modernization a necessary evolution to ensure global stability? Or is the $141 billion price tag a symptom of an industrial base that has lost its way? Is it possible for a 50-year-old infrastructure to truly be brought into the digital age? Let us know your thoughts in the comments below. And if you want to see the industrial secrets behind the Silicon Shield or the Golden Dome air defense systems, don't forget to hit like and subscribe for our next deep dive into the machines that shape our world.